Hello there. Welcome to Info Jungle. This is where curiosity slows down, where the world feels a little quieter. Tonight, we're heading into a place that feels ancient, a place strangely untouched by time, a place where the surface world fades away, replaced by pressure, replaced by darkness, replaced by life, shaped by forces we barely understand. But before we go any deeper, I'd like to know something grounding. Where are you watching from tonight? And what time is it for you? Your check-ins always feel like small warm lights scattered across the darkness. Each one a reminder that while we drift into hidden places, you're somewhere safe. Somewhere steady. Somewhere still. If slow science, quiet exploration, and gentle deep-sea journeys help you rest, feel free to like the video. Or subscribe. Only if it feels right for you. This is a calm corner of the internet. Nothing here happens in a rush. There is a place on our planet that remains more mysterious than the surface of Mars. It sits beneath miles of ocean. We know it exists. We can measure its depth. But we cannot stay there. The Mariana Trench lies in the western Pacific Ocean. It stretches for over 1,400 miles. At its deepest point, the seafloor drops nearly 7 miles below the surface. If you placed Mount Everest at the bottom, its peak would still rest a mile underwater. This is not empty space. It is water. And water has weight. Think about that for a moment. Water seems light when you hold it in your hands. A glass weighs almost nothing. A bucket can be lifted easily. But when water gathers in vast quantities, when it stacks mile upon mile, it becomes something else entirely. Every 10 meters you descend adds another atmosphere of pressure. At the surface, air presses on your skin with a force of 14.7 pounds per square inch. You never notice it. Your body evolved to balance against it. The air inside your lungs pushes outward with equal force. Everything stays in equilibrium. But underwater, that balance disappears quickly. At 30 feet down, pressure doubles. At 100 feet, it triples. Most recreational divers never go deeper than this. The body can adapt to these depths with proper training and equipment. But there are limits. At 100 meters, pressure increases 10 times what you feel at the surface. At this depth, nitrogen begins to act strangely in your bloodstream. It can cause confusion, euphoria, even unconsciousness. Divers call it nitrogen narcosis. The deeper you go, the worse it becomes. At 1,000 meters, pressure becomes truly crushing. Steel begins to feel the strain. Submarine hulls must be reinforced. Air spaces compress to almost nothing. Even specially designed equipment starts to show signs of stress. By the time you reach the bottom of the trench, at nearly 11,000 meters, the pressure exceeds 16,000 pounds per square inch. That is the weight of 3 small cars pressing on every square inch of surface area. Or imagine 50 jumbo jets stacked on top of you. That is what the water column creates at that depth. Steel bends under that force. Concrete crumbles. Glass shatters. Air compresses into almost nothing. Even materials we think of as solid begin to behave differently. Molecules get forced closer together. Chemical bonds strain. Structures that seem permanent at the surface become fragile in the deep. This is why we cannot simply visit the deepest ocean. The environment does not permit it. Every attempt to go there requires years of engineering, months of testing, careful planning of every detail. And even then, every dive carries risk. Every descent is a gamble against forces that could destroy any vessel in an instant. And yet, despite these dangers, people keep trying. Because the trench represents something fundamental about exploration itself. It is a place that exists on our planet, within our reach in theory, yet almost completely beyond our grasp in practice. The trench does not resist us out of hostility. It is not an enemy. It does not actively try to keep us away. It simply exists under conditions that human bodies were never built to withstand. Conditions that challenge our best technology. Conditions that force us to recognize our own fragility. We are creatures of the surface. We evolved in air under normal pressure, with access to light and warmth. The deep ocean is the opposite of everything our bodies need. It is cold where we need warmth, dark where we need light, pressurized where we need space to breathe. And that is where our story begins. Not with what we have discovered in the trench, but with what continues to stop us from learning more. Not with triumph, but with limitation. Not with conquest, but with humility. The ocean covers more than 70% of Earth's surface. It contains 97% of all water on the planet. And most of that water sits in depths we have never seen. Will probably never see. The average depth of the ocean is over 12,000 feet. Most of it exists in permanent darkness. When we look at the night sky and feel small beneath the stars, we are looking at vast distances. But those distances are empty. The ocean is different. It is not empty. It is full, dense, heavy, and it presses down with a weight that increases with every meter of depth. The Mariana Trench is where that weight reaches its maximum. It is the lowest point in the entire ocean, the deepest scar on the face of our planet. And it sits there quietly, patiently, without needing our attention or understanding. For most of human history, we did not even know it existed. Ships sailed above it without realizing what lay beneath. Sailors told stories of bottomless seas, of waters so deep that no line could ever measure them. In a way, they were not entirely wrong. It was not until the development of sonar in the 20th century that we began to understand the true shape of the seafloor. Before that, depth measurements were done by dropping weighted lines over the side of ships. The line would sink until it hit bottom. Then it would be pulled back up and measured. This method was slow and imprecise. In deep water, currents could carry the line sideways. It might never reach bottom at all. Or it might touch down, but the crew could not tell for certain. The ocean kept its depth secret. But sonar changed everything. Sound waves could be sent downward. They would travel through water, bounce off the seafloor, and return. By measuring the time it took for the echo to come back, scientists could calculate depth with much greater accuracy. And that is how we discovered just how deep some parts of the ocean truly are. The Mariana Trench revealed itself not through direct observation, but through echoes, through sound bouncing back from places no human eye had ever seen. Even now, with all our technology, we rely on indirect methods. We map the seafloor with sonar. We send cameras into the dark. We collect samples with robotic arms. But we rarely go there ourselves. And when we do, we go briefly, carefully, and we return as quickly as conditions allow. The weight of water defines everything about the trench. It shapes what can live there, what can survive, what can be explored. It is the fundamental barrier that separates our world from that one. And it is a barrier we cannot simply remove. We cannot make water lighter. We cannot reduce the pressure. We cannot change the basic physics that govern how fluids behave under compression. What we can do is build machines that can withstand it. We can design vessels that distribute pressure evenly. We can use materials that do not fail under extreme load. We can plan carefully, test thoroughly, and hope that our calculations are correct. But even with perfect engineering, the ocean imposes limits. Time limits, energy limits, human endurance limits. The deeper we go, the more expensive it becomes. The more dangerous, the more isolated we are from any possibility of rescue. This is why exploration of the Mariana Trench has been so limited. Not because we lack curiosity, not because we lack the will to go, but because the ocean itself says no. Or more accurately, it says you may enter, but only on my terms. Only for a short time. Only if you are very, very careful. And those terms are strict. They do not negotiate. They do not bend. They are written in the physics of pressure and depth, in the weight of miles of water pressing downward, in the simple, undeniable fact that some environments are not built for us. The trench is one of those places. It exists. We can touch it, but we cannot stay. And that limitation is what this story is really about. Understanding why the trench is so difficult to reach starts with understanding what it actually is. Not just a deep spot in the ocean, but a geological feature shaped by forces that have been at work for millions of years. The Mariana Trench formed where two massive plates of Earth's crust meet. The Pacific Plate slides slowly beneath the smaller Philippine Plate. This process happens at a rate of about 2 to 3 inches per year. It sounds slow, and it is. But over millions of years, that slow movement creates dramatic changes. Geologists call this subduction. One plate dives under another. The edge of the descending plate bends downward. Rock melts. Magma rises. Volcanoes form. And along the boundary where the plates meet, a deep trench opens. This is not a sudden event. It is not a crack that appeared overnight. The trench has been forming for tens of millions of years. And it is still forming now. The plates are still moving. The trench is still deepening. Though at a pace so slow we cannot perceive it in a human lifetime. The trench itself runs roughly north to south. It curves gently, following the line where the two plates meet. At its widest point, it spans about 43 miles, but most of its length is much narrower. In some places, the walls of the trench rise steeply on either side, like a canyon carved into the ocean floor. This is not a straight drop into blackness. The descent is gradual in places, steep in others. The walls are made of volcanic rock, sediment, and hardened lava. In some areas, the slope is gentle enough that sediment has accumulated, creating smooth surfaces. In other areas, jagged cliffs fall away into darkness. The deepest part is called Challenger Deep. It was named after the HMS Challenger, a British research ship that conducted oceanographic surveys in the 1870s. During one of their measurements in the Western Pacific, they recorded a sounding of over 8,000 meters. At the time, it was the deepest measurement ever taken. Modern instruments have refined that number. Challenger Deep sits at approximately 10,920 meters below sea level. That is nearly 11 kilometers, or about 6.8 miles. To put that in perspective, commercial airplanes typically cruise at around 35,000 feet. That is about 6.6 miles. The bottom of the trench is deeper below sea level than a cruising airliner is above it. At that depth, conditions are extreme. Temperature hovers just above freezing, around 1 to 4 degrees Celsius. It never gets warmer. There is no seasonal variation. The cold is constant. No sunlight penetrates. Light from the surface fades within the first few hundred meters. By the time you reach 1,000 meters, it is completely dark. And Challenger Deep is 10 times deeper than that. The darkness there is absolute. It has been dark for as long as the trench has existed. The water is still in the sense that there are no waves. But it is not motionless. Currents move through the trench, though slowly. Water circulates. It carries nutrients, particles, and dissolved gases. The trench is not isolated from the rest of the ocean. It is connected to every current, every temperature layer, every chemical cycle that operates in the sea. But the stillness is what strikes most people. When cameras are sent down, they often show sediment lying undisturbed. Small ripples in the mud, frozen in place. The water so calm that particles drift slowly, without any obvious direction. It is a quiet place, but not silent. Sound travels differently in the trench. It moves faster through dense water than it does through air. And at depth, water is extremely dense. This means that low-frequency sounds, vibrations from distant sources, can travel for hundreds or even thousands of miles. The ocean transmits the groans of shifting tectonic plates, the rumble of underwater landslides, the calls of whales from the surface, layers far above. Even the faint echoes of storms happening thousands of miles away can be detected if you have sensitive enough instruments. The trench is not separate from the ocean above it. It is the lowest part of a continuous system. Water that starts at the surface eventually sinks. Currents carry it downward. It brings oxygen, nutrients, and particles with it. That water may take decades or centuries to complete its journey. But eventually, some of it reaches the trench. And when it does, it joins a slow circulation. Water that enters the trench does not stay there forever. It mixes. Gradually, it rises again. It might emerge thousands of miles away, decades or centuries later. But it returns. This circulation is part of what scientists call the global conveyor belt, a system of ocean currents that connects every part of the sea. Warm water flows near the surface. Cold water sinks and flows along the bottom. Over time, the entire ocean cycles through this system. The trench is part of that cycle. It is not isolated, not cut off. It is connected to everything else. And that connection matters. When scientists study the trench, they are not just studying a remote location. They are studying a system, a process, a piece of the puzzle that helps us understand how the entire ocean works. But getting to the trench is not easy. It sits in the middle of the Pacific, far from any major landmass. Reaching it requires a research vessel capable of handling rough seas, equipment that can operate in deep water, and time. Lots of time. A typical expedition might take weeks just to reach the site, then more weeks to conduct dives, and more weeks to return. The journey itself is a challenge. The ocean between the surface and the trench is not a void. It is a series of layers, each with its own temperature, salinity, and density. Navigating through those layers requires care. And then there is the simple fact that the trench is huge. It stretches for over 1,400 miles. Even if you could explore it thoroughly, which you cannot, it would take years to survey the entire length. Most expeditions focus on small sections, a few square kilometers at most. What we know about the trench comes from these small glimpses, brief visits to isolated spots. We have maps of the general shape. We know where the deepest points are, but the details are sparse. Most of the trench has never been photographed, never been sampled, never been touched by human-made instruments. It remains, for the most part, unknown. And that is part of what makes it compelling. It is not a mystery because it is hidden. It is a mystery because it is so difficult to reach, so expensive to study, so resistant to the kinds of detailed exploration we can do on land. When you look at a map of the Mariana Trench, you see a narrow curve on the ocean floor. It looks small on a map, but in reality, it is enormous. And it contains environments, species, and processes we barely understand. The geography of the trench is not just about depth. It is about isolation, about pressure, about conditions that push the boundaries of what life can tolerate. And it is about the simple fact that some places on Earth remain beyond our easy reach. We have climbed the highest mountains. We have crossed the driest deserts. We have ventured to the coldest places on the continent. But the deepest ocean still holds us at arm's length. It allows brief visits, but it does not allow us to stay. And perhaps that is appropriate. Perhaps some places should remain mostly unknown, not because we are incapable of exploring them, but because the cost of doing so is so high that we must be selective. We must choose our visits carefully, make them count, and accept that most of the trench will remain, for now and perhaps forever, a place we can only imagine. To understand why exploration is so limited, you need to understand what pressure actually does. Not just as an abstract concept, but as a physical force that changes how materials behave. Imagine holding a steel ball in your hand. It feels solid, permanent, immovable. The metal is dense and strong. You could drop it and it would not deform. You could hit it with a hammer and it would barely dent. But at extreme depth, even steel changes. The molecular structure begins to compress. The spaces between atoms shrink. Tiny imperfections in the metal, flaws that are invisible at the surface, become weak points. Under enough force, the ball would collapse inward. Not quickly, not dramatically, but gradually the structure would fail. This is not a flaw in the steel. It is simply physics. All materials have limits. All structures eventually reach a point where external pressure exceeds internal strength. And when that happens, they fail. Pressure does not push from one direction. It does not act like a weight sitting on top of something. Instead, it presses equally from all sides. From above, below, left, right, front and back. In the trench, every surface of an object experiences the same crushing force from every angle. This makes pressure particularly difficult to resist. You cannot brace against it in one direction. You cannot build a structure that is only strong on top. The pressure finds every weakness, every gap, every surface, and it pushes inward without pause. For human bodies, this creates immediate problems. We are mostly water, and water, unlike air, does not compress easily. The liquid inside our cells, our blood, our tissues, all of this resists compression fairly well. But our bodies also contain air spaces. Our lungs are filled with air. Our sinuses contain air. There are small pockets of gas in our intestines. And all of these spaces would collapse instantly at depth. At just a few hundred meters, the air in your lungs would compress to a fraction of its normal volume. Your chest would cave inward. Your ribs would fracture. Blood vessels in your lungs would rupture. And even if you somehow survived that, the gases dissolved in your blood would begin to cause other problems. Nitrogen, which makes up most of the air we breathe, dissolves into the bloodstream under pressure. The deeper you go, the more nitrogen enters your blood. When you ascend, that nitrogen needs to come back out. If you rise too quickly, it forms bubbles. Those bubbles can block blood vessels, cause strokes, damage tissues. This is what divers call the bends. And it can be fatal. Even if we somehow solved the problem of air spaces, the cold would stop us. At the bottom of the trench, water temperature hovers just above freezing. Human bodies cannot tolerate that kind of cold for long. Muscles lose function. Blood thickens. Nerve signals slow. Consciousness fades. We would need protection from the pressure and insulation from the cold. And we would need to breathe. But bringing air with us means carrying something that compresses. Something that becomes dangerous under pressure. This is why human exploration of the trench is so rare. Our bodies are simply not built for it. We are creatures adapted to atmospheric pressure, to temperatures well above freezing, to environments where we can breathe freely. The deep ocean is the opposite of all of that. And no amount of training can change our fundamental biology. We can hold our breath longer. We can tolerate cold better. But we cannot change the fact that pressure at those depths would kill us in seconds. So we build machines to go in our place. Vessels that can withstand pressure. That can protect the fragile air spaces inside. That can descend and return safely. But building such machines is extraordinarily difficult. Every surface must be perfect. Every joint sealed completely. Every material chosen for its ability to resist compression. And even then, the machines have limits. They can go deeper than we can. But they cannot go everywhere. They cannot stay indefinitely. And they cannot explore freely. Pressure also affects how things function. Electronics, for example, behave differently under load. Circuit boards can crack. Solder joints can fail. Insulation can compress, causing shorts. Batteries drain faster in the cold. Motors struggle to turn when lubricants thicken. Even simple mechanical systems become complex at depth. A hinge that works perfectly at the surface might seize up under pressure. A valve that opens easily on land might require far more force to move when surrounded by dense water. This means that every component of a deep-sea vehicle must be tested, not just in a laboratory, but under conditions that simulate the actual environment. Pressure chambers can recreate the forces. Cold rooms can test temperature tolerance. But nothing fully replicates the combination of pressure, cold, darkness, and salt water except the ocean itself. And that testing is expensive, time-consuming, and risky. A component might pass all tests and still fail during an actual dive. The ocean is unpredictable in ways that laboratories are not. Then there is the problem of communication. At depth, radio signals do not work. Radio waves cannot penetrate water effectively. They are absorbed within meters. This means that a submersible at the bottom of the trench cannot use radio to talk to the surface. Instead, communication happens through sound. Acoustic signals, like underwater Morse code. A transmitter sends pulses of sound. Those pulses travel through the water. They reach a receiver. The receiver interprets them as data. But sound travels slowly compared to radio. A message from the surface to the bottom of the trench takes several seconds to arrive. The reply takes several more seconds to return. This creates a delay that makes real-time control impossible. If something goes wrong at depth, there is no way to react quickly. No way to send immediate help. The submersible is on its own. It must be able to handle any problem that arises without outside assistance. And that means every system must be redundant. Every critical function must have a backup. Batteries must last longer than the dive is expected to take. Life support must have reserves. Ballast systems must be able to drop weight even if power fails. The ocean does not forgive mistakes. At the surface, if something breaks, you can improvise. You can call for help. You can swim to shore. But at 11,000 meters, if something fails, there are no options. No rescue. No second chances. The pressure sees to that. It makes every flaw fatal. Every error catastrophic. And that is why exploration is so limited. Not because we lack the desire to go, but because the environment is so hostile that only the most carefully prepared, thoroughly tested, perfectly functioning systems can survive. And even then, survival is measured in hours. Not days. Not weeks. Just a few hours at the bottom before the ascent must begin. Before batteries run low. Before the weight of uncertainty becomes too great. Pressure shapes everything about how we explore the trench. It determines what vehicles we build, how long we can stay, what we can study, and how much risk we are willing to accept. It is the fundamental barrier, the wall that cannot be removed. And it is why, despite all our advances, the deepest ocean remains one of the least explored places on Earth. The first humans to reach the bottom of the Mariana Trench did so in 1960. The vessel they used was called Trieste, and it represented a bold gamble against the crushing pressure of the deep. Trieste did not look like a modern submarine. It was not sleek, not streamlined, not built for speed or maneuverability. Instead, it was designed for one purpose only: to descend to the deepest point in the ocean and return. The basic design was simple in concept, but complex in execution. At the top sat a large float. This float was filled with gasoline, not for fuel, but for buoyancy. Gasoline is lighter than water, and unlike air, it does not compress significantly under pressure. This made it ideal for maintaining buoyancy at depth. Beneath the float hung a thick steel sphere. This sphere was where the crew sat. It was small, just wide enough for two people to sit side by side. The walls were made of forged steel, 5 inches thick. The weight of the sphere alone was several tons. Inside that sphere, the air pressure remained normal, breathable. The thick walls kept the crushing pressure of the ocean outside. They distributed the force evenly across the curved surface. A sphere is one of the strongest shapes for resisting external pressure. Any flat surface would buckle, but a sphere pushes back equally in all directions. The sphere had small windows, cones of plexiglass several inches thick. Even with that thickness, the windows were a potential weak point. Pressure could crack them. Water could seep through. The men inside would have only seconds to react if a window failed. On January 23, 1960, 2 men climbed into that sphere. Jacques Piccard, a Swiss oceanographer and engineer, and Don Walsh, a lieutenant in the United States Navy. They sealed the hatch. The support crew checked every system, and then Trieste began its descent. The journey down took nearly 5 hours. The men inside could not see much through the tiny viewports. At first, sunlight filtered down from above. The water glowed blue, then green, then dim, and then black. Temperature inside the sphere dropped. The men wore layers of clothing. Their breath fogged in the cold. The only sounds were the faint hum of instruments and the occasional creak of metal adjusting to pressure. They watched the depth gauge, numbers climbing slowly. 1,000 meters, 2,000, 3,000. The pressure outside increased with every passing minute. The walls of the sphere groaned softly. This was normal, expected, but unnerving nonetheless. At around 9,000 meters, they heard a sharp crack. Something had broken. They were not sure what. Later, they discovered that one of the outer windows had fractured. Not the main viewport into their sphere, but a window in the entry tube above them. It was not an immediate danger, but it was a reminder of how fragile their vessel was. Still, they continued. There was no turning back. Not after coming this far. Finally, after nearly 5 hours, they felt a gentle bump. Sediment appeared in the lights outside. They had reached the bottom, 10,911 meters below the surface, the deepest anyone had ever been. They stayed for only 20 minutes, long enough to take a few photographs, to confirm that they had made it, to record some basic observations. And then they began the long ascent. The return took over 3 hours. Slowly, carefully, Trieste rose through the darkness. The pressure decreased gradually. The temperature warmed slightly. And eventually, they saw light filtering down from above. First a faint glow, then brighter. And finally, they broke the surface. When the hatch opened, sunlight and fresh air flooded in. The dive was over. They had proven something important. It was possible for humans to reach the deepest part of the ocean and survive. But the dive also revealed how difficult such a journey was. The entire mission had taken nearly 9 hours. Most of that time was spent descending or ascending. Only a few minutes were spent actually exploring the bottom. And the technology required was massive. Trieste was not a portable device. It required a large ship to transport it, cranes to lower it into the water, a crew of dozens to support the operation, and enormous cost. The development and deployment of Trieste represented years of work and significant financial investment. Since 1960, technology has improved. Materials have gotten stronger. Electronics more reliable. Power systems more efficient. But the core challenge has not changed. Modern submersibles still use spherical pressure hulls. Many are made of titanium instead of steel. Titanium is stronger and lighter. It resists corrosion better in salt water, and it can be machined to very precise tolerances. The spheres are still small. Most modern deep-sea submersibles carry 1 to 3 people. The space inside is cramped. There is barely room to move. You sit in a fixed position for hours, monitoring instruments, adjusting controls, watching through small viewports as the deep reveals itself slowly. Some modern vehicles are unmanned. Remotely operated vehicles, or ROVs. These are controlled from a ship at the surface. They carry cameras, lights, sensors, and mechanical arms. They can collect samples, record video, measure temperature and chemical composition. ROVs have advantages. They do not risk human lives. They can stay at depth longer. They do not need life support systems. And they can be smaller and more maneuverable than crewed vehicles. But they also have limitations. They are tethered to the ship above by long cables. These cables carry power and communication signals. But they also create drag. They can get tangled. They limit how far the ROV can roam. And if the tether breaks, the ROV is lost. There is no way to recover it. The ocean keeps what it takes. Some newer vehicles are autonomous. They are not tethered. They operate independently, using onboard batteries and pre-programmed instructions. They can explore on their own, navigate around obstacles, collect data without constant supervision. But autonomous vehicles have their own challenges. Batteries limit how long they can operate. And at depth, batteries drain faster. The cold affects chemical reactions. Power output drops. Communication is also difficult. Without a tether, the only way to send signals is through sound. And acoustic communication is slow, limited, prone to interference from ocean noise. So even with all our advances, deep-sea vehicles are limited in what they can do. They can descend. They can observe. They can collect samples. But they cannot stay indefinitely. They cannot explore freely. And they cannot guarantee success. Every dive is a carefully planned operation. Weather must cooperate. Seas must be calm enough to launch and recover the vehicle. Equipment must function perfectly. And even then, things can go wrong. Batteries can fail. Seals can leak. Electronics can malfunction. Thrusters can jam. Any one of these problems can end a dive early. Or worse, strand the vehicle at depth. The ocean does not care how much money you spent building your machine. It does not care how many tests you ran. It judges every vehicle by the same standard. Can it withstand the pressure? Can it function in darkness and cold? Can it return? If the answer to any of those questions is no, the ocean takes the vehicle. And there is no appeal. No second chance. This is why only a handful of vehicles have ever reached the bottom of the Mariana Trench, and why even fewer have returned with useful data. The barriers are not just technological. They are fundamental, built into the physics of the deep ocean. We keep building better machines, stronger materials, smarter systems, and slowly we push a little deeper, stay a little longer, learn a little more. But progress is measured in decades, not years. Each new generation of vehicles represents a small step forward, a slight improvement, a marginal increase in capability. And that is the reality of deep-sea exploration. It is not dramatic, not fast, not easy. It is slow, careful, expensive work, done by small teams, over long periods, with frequent setbacks and rare successes. The machines we build are marvels of engineering. They represent the best of human ingenuity and determination. But they are also reminders of our limitations. Reminders that some environments remain hostile to us, no matter how clever our tools become. And the Mariana Trench remains one of those environments. A place we can visit briefly, but never inhabit. Never truly explore the way we explore mountains or forests or even other planets. The machines give us access, but only conditional access. Only temporary. Only at great cost and with significant risk. And perhaps that is how it should be. Perhaps some places should remain difficult to reach, not as a challenge to overcome, but as a reminder of where we belong and where we do not. While we struggle to survive even for moments at the bottom of the trench, life has been there for millions of years, thriving, adapting, continuing without pause. When scientists first began exploring the deep ocean, the prevailing theory was that nothing could live below a certain depth. The pressure seemed too extreme, the cold too severe, the darkness absolute, food scarce, oxygen limited. It seemed impossible that any organism could tolerate such conditions. But they were wrong. The first hint came in the 1870s, when the HMS Challenger expedition pulled up samples from great depths. They found life. Not just bacteria, but complex organisms, small crustaceans, strange worms, creatures that should not have been able to exist. This discovery changed everything. It forced scientists to rethink what life required, to question their assumptions about biological limits, and to wonder what else might be living in places we had declared lifeless. As technology improved and cameras reached deeper waters, the pictures they sent back were startling. The deep ocean was not a desert. It was an ecosystem, different from anything on land, different from shallow seas, but alive nonetheless. At the bottom of the Mariana Trench, in water that would crush a submarine, life continues. Small pale creatures drift through the sediment. Fish with soft, transparent bodies glide through the darkness. Shrimp scavenge for food particles. Worms burrow into the mud. These organisms are not struggling. They are not barely surviving. They are at home. This environment, so hostile to us, is normal to them. They were born here. They have lived here for generations, stretching back millions of years. And they will continue after we are gone. Their bodies have adapted in ways that seem almost impossible to comprehend. They do not fight against pressure. They exist in balance with it. The water outside their bodies is at the same pressure as the water inside. There is no gradient pushing inward. No force trying to crush them. Their cells contain special molecules, proteins that remain stable under pressure, membranes that do not collapse, chemical reactions that function normally even when compressed. These adaptations took millions of years to evolve. But now they work perfectly. Many of these creatures have no bones. Or if they do, the bones are soft, flexible, more like cartilage than the rigid skeletons we are familiar with. Hard structures would be a liability here. They would resist pressure instead of accommodating it. And resistance leads to failure. Flexibility is survival. Bodies that bend rather than break. Tissues that compress slightly without damage. Systems that operate under forces that would kill surface dwellers instantly. Take the snailfish, for example. These small pale fish have been found at depths exceeding 8,000 meters. Their bodies are soft, almost gelatinous. Their skin is loose and wrinkled. They look fragile, but they are anything but. Inside their cells are molecules called osmolytes. These compounds stabilize proteins under pressure. They prevent the normal breakdown that would occur in other organisms. The snailfish essentially has built-in antifreeze for pressure, chemical protection that allows it to function where other vertebrates cannot. And it is not alone. Amphipods, small crustaceans related to shrimp, have been found throughout the trench. Some grow to surprising sizes, several inches long, far larger than their shallow water cousins. They scavenge the seafloor, feeding on whatever organic material drifts down from above. These amphipods have reinforced exoskeletons. But the reinforcement is not rigidity. It is aluminium. Aluminium compounds incorporated into their shells make them stronger without making them inflexible. The metal helps distribute pressure more evenly. Another elegant adaptation to an extreme environment. Then there are the microorganisms, bacteria and archaea that live in the sediment itself. These single-celled organisms are even more remarkable. They survive not only the pressure and cold, but also the lack of oxygen and nutrients. Some of these microbes feed on chemicals. They break down organic compounds that drift down from the surface. Others rely on chemosynthesis. They extract energy from chemical reactions between water and rock. They do not need sunlight, do not need oxygen. They exist on chemistry alone. When scientists brought samples of sediment back from the trench and examined them under microscopes, they found billions of these microbes. Not dormant, not barely alive, but active, reproducing, metabolizing, living their microscopic lives in mud that sits under 7 miles of water. This discovery has implications beyond the trench. If life can exist under such extreme conditions on Earth, where else might it exist? On other planets, other moons, in places we once thought too harsh for biology. Europa, one of Jupiter's moons, has an ocean beneath its icy crust. That ocean is under pressure. Cold, dark. But if life can thrive in the Mariana Trench, perhaps it could thrive in Europa's ocean as well. Enceladus, a moon of Saturn, also has subsurface water, hydrothermal vents, chemical gradients, conditions not unlike those found in Earth's deep ocean. The creatures of the trench suggest that such environments might not be lifeless after all. But back on Earth, the adaptations continue to surprise us. Many deep-sea creatures produce their own light. In a world without sun, bioluminescence becomes essential. It is used for hunting, for communication, for defense, for finding mates in the vast darkness. Some fish have lures that glow. They dangle from their heads like fishing rods. The light attracts smaller fish. When prey gets close enough, the predator strikes. It is efficient, economical. No wasted energy chasing food through the dark. Other creatures use light defensively. When threatened, they release bursts of bioluminescent chemicals. The sudden flash blinds or confuses predators, giving the prey time to escape into the darkness. Jellyfish drift through the water, their bodies glowing faintly. The light is not bright, just a soft blue or green luminescence. But in total darkness, it is visible from surprising distances. Other jellyfish see it. Predators see it. And the message is clear. I am here. Even bacteria glow. Some form symbiotic relationships with larger organisms. They live inside fish or squid, producing light in exchange for food and shelter. The host provides nutrients. The bacteria provide illumination. Both benefit. This bioluminescence is remarkably efficient. It produces almost no heat, just pure light. The chemical reactions involved are so refined that nearly all the energy goes into photons, not wasted as thermal radiation. On land, artificial lights are inefficient. Incandescent bulbs waste most of their energy as heat. Even LEDs lose some energy. But bioluminescence achieves what our technology cannot: perfect conversion of chemical energy into light. The food chain in the trench is unlike anything on the surface. There are no plants. Photosynthesis is impossible without sunlight. So the base of the food web is not green. It is brown and grey, made of detritus. Scientists call it marine snow. It is a constant, slow rain of organic particles drifting down from the surface. Dead plankton, fish scales, fecal pellets, fragments of larger animals. Anything organic that dies near the surface eventually sinks. This debris takes weeks or months to reach the bottom. As it falls, it is consumed by creatures living at intermediate depths. What remains gets smaller, more processed. By the time it reaches the trench, it is barely recognizable as biological material. But it still contains energy. And that energy is precious. Creatures on the seafloor feed on this marine snow. They filter it from the water, sift it from the sediment, extract every calorie they can. Nothing is wasted, because waste means starvation. Occasionally, something larger arrives. A dead whale, a large fish. When this happens, it becomes an event. Scavengers from miles around converge on the carcass. They feed for weeks, sometimes months, until nothing remains but bones. Even the bones are consumed eventually. Bacteria colonize them, breaking down the minerals, extracting the last traces of organic material. In the trench, everything gets used. Everything gets recycled. The cycle is slow but thorough. Energy is so scarce that predation happens slowly as well. Fish do not chase prey at high speed. They wait. Conserve energy. Strike only when success seems certain. Every movement costs energy. Energy that might not be replaceable for days or weeks. This creates a strange ecosystem, one where patience is the primary survival strategy, where speed is a liability, where doing nothing is often the best choice. Reproduction follows the same pattern. Many deep-sea creatures reproduce slowly. They lay few eggs. Invest heavily in each offspring. Give them the best chance possible to survive in an environment that offers no second chances. Some species lay eggs that develop over months, even years. The embryos grow slowly in the cold, taking their time. There is no rush, no seasonal pressure, no reason to hurry. Others give birth to live young, already formed, ready to survive. This ensures that the next generation starts with the best possible advantages. In a place where food is scarce and danger constant, this investment pays off. But despite all these adaptations, despite millions of years of evolution, the creatures of the trench remain vulnerable. Not to pressure or cold or darkness, but to us. In recent years, scientists have found plastic in the bodies of amphipods collected from the deepest parts of the ocean. Microplastics, tiny fragments that have drifted down from the surface, consumed by mistake, accumulating in tissues. These plastics do not belong there. They are not part of the natural cycle. They do not break down easily, and their long-term effects on deep-sea life are unknown. Chemical pollutants have been found as well. Traces of industrial compounds in sediment cores. Proof that even the most remote environment on Earth is not beyond our reach. Not safe from contamination. The creatures that have survived millions of years of pressure and darkness now face something new. Something they did not evolve to handle. Human waste. Human chemicals. Human debris. And unlike pressure, there is no adaptation for this. No evolutionary solution. The plastic keeps coming. The chemicals keep sinking. And the deep ocean absorbs it all. But for now, life continues. The snailfish still glide through the darkness. The amphipods still scavenge the seafloor. The bacteria still process what falls from above. They do not know about the plastic, do not understand the threat. They simply continue living as they have always lived. And in that continuation, there is something both beautiful and fragile. These creatures represent life's ability to persist in the most unlikely places. But they also remind us that persistence has limits, that even the deepest ocean is not separate from the world above. What happens on the surface eventually reaches the bottom. The trench is not isolated. It is connected. And that connection means we carry responsibility for what we send into the deep. Exploration at these depths is not just difficult. It is expensive, prohibitively so for most organizations. And that cost is one of the main reasons we know so little about the trench. A single mission to the Mariana Trench can cost millions of dollars. sometimes tens of millions. This is not a figure that includes scientific salaries or years of preparation. This is just the cost of the expedition itself. The ship, the equipment, the fuel, the crew, the support infrastructure. Consider what is required. First, you need a research vessel. Not just any boat, but a ship large enough to carry a submersible or ROV. Strong enough to handle rough seas. Equipped with cranes, winches, and launch systems capable of lowering heavy equipment into the ocean. Such ships are rare. Expensive to build. Expensive to maintain. Expensive to operate. Fuel alone can cost thousands of dollars per day. And a single expedition might take months. From departure to return. Then you need the submersible itself. This is where costs escalate dramatically. Designing a vehicle capable of reaching the bottom of the trench requires years of engineering. Every component must be custom built, tested, certified. The pressure hull alone costs hundreds of thousands of dollars. It must be machined to precise tolerances. Any imperfection could be a weak point. Any miscalculation could lead to catastrophic failure. So every step is checked, rechecked, verified by independent engineers. The electronics must be specially designed. Standard components cannot withstand the pressure, even when housed in sealed containers. So manufacturers create custom systems, pressure-resistant sensors, reinforced circuit boards, specialized connectors that can handle both electrical current and extreme compression. Cameras must be enclosed in thick housings, made of materials that remain transparent under pressure. Sapphire is often used for lenses. It is strong, clear, resistant to scratching, but also expensive. Lights must be powerful enough to illuminate the darkness, but also efficient enough not to drain batteries too quickly. LED technology has helped with this, but deep sea lights are still custom built, sealed in titanium housings, tested to ensure they do not implode at depth. Life support systems add more cost. Even unmanned vehicles need power. Batteries that can function in near freezing temperatures, that do not lose capacity under pressure. Lithium-ion batteries have limitations at depth, so engineers develop specialized power systems, often using materials and designs that exist nowhere else. Thrusters allow the vehicle to maneuver, but they must work against dense water, against currents that push in unexpected directions. Motors must be powerful but efficient. Propellers must be designed to move water effectively at high pressure. Every component optimized for an environment that punishes inefficiency. Communication systems add another layer of complexity. Acoustic modems are not cheap. They require sophisticated signal processing, error correction, protocols that can handle delays and distortion. Each unit costs tens of thousands of dollars, and you need multiple units. One on the vehicle, one on the ship, often backups in case of failure. Then there is the question of testing. Before any vehicle can dive to the trench, it must be tested. Repeatedly, thoroughly, in controlled environments first, then in progressively deeper water. Pressure chambers simulate the forces at depth, but chamber time is expensive. The facilities are booked months in advance. Each test session costs thousands of dollars, and you might need dozens of sessions before you are confident the vehicle will survive. Shallow water tests follow, deploying the vehicle in water a few hundred meters deep, checking systems, looking for leaks, verifying that everything functions as expected. Each test requires ship time, crew time, fuel, days or weeks of careful evaluation. Only after all this can you attempt a deep dive. And even then, there is no guarantee of success. The first attempt might reveal problems, require modifications, more testing, more time, more money. Personnel costs add up as well. You need engineers to maintain the equipment, pilots trained to operate the submersible, scientists to analyze data, support crew to handle launches and recoveries. Each person must be paid, fed, housed, transporting to and from the research site. A typical deep-sea expedition might involve 30 to 50 people. For weeks or months. Salaries, travel expenses, insurance. All of this adds to the total cost. And then there is the risk. Equipment can be lost. A submersible that costs millions can fail at depth, never return, be lost forever to the ocean floor. Insurance helps, but it does not cover everything. And it does not reduce the emotional and professional cost of losing years of work in an instant. This is why only a handful of organizations have ever sent missions to the Mariana Trench. Government agencies, research institutions, a few wealthy individuals with personal interest in exploration. The barriers to entry are simply too high for most groups. Compare this to space exploration. NASA's budget is measured in billions, but those billions fund hundreds of missions, thousands of scientists, decades of research. Deep-sea exploration has no equivalent funding, no equivalent infrastructure, no equivalent public support. When a rocket launches, people watch. News cameras cover it. Children dream of being astronauts. There is excitement, prestige, national pride. When a submersible descends to the trench, almost no one notices. The work happens quietly, in remote locations, far from cameras and attention. This lack of public interest translates to lack of funding. Governments allocate resources based on priorities. And deep-sea research for most countries is not a top priority. The money goes elsewhere. To defense, to healthcare, to programs with more visible benefits. Private funding helps, but it is limited. A wealthy individual might fund one expedition, but sustained exploration requires sustained funding. Year after year, expedition after expedition. And that level of commitment is rare. Some people ask why we do not build permanent stations at the bottom of the trench, underwater bases that could support long-term research. The answer is cost and technical difficulty. Building a structure that could withstand pressure at those depths would be enormously expensive. Maintaining it would be nearly impossible. Every component would degrade over time. Seals would need replacement. Systems would fail. And resupply missions would be dangerous and costly. The International Space Station costs over $100 billion to build and maintain. And it operates in an environment that is, in many ways, easier to work in than the deep ocean. There is no pressure in space, no corrosion, no water to leak through every seal. An equivalent station at the bottom of the trench would face far greater challenges and would cost far more. Money that does not currently exist and is unlikely to be allocated in the near future. So for now, exploration remains limited. A few expeditions per decade, brief visits to isolated locations, small samples collected, short videos recorded, and then departure. Back to the surface, back to the world of air and light. The cost ensures that most of the trench remains unexplored, unseen, unknown, not because we lack the technology, but because we lack the resources to use that technology widely. And perhaps that is another reason the trench remains mysterious. Not because it is inherently unknowable, but because knowing it would require an investment we are not yet willing to make. Beyond the physical and financial challenges, there is another reason we struggle to explore the trench. It is psychological, and it affects everyone who attempts to go there. Descending into total darkness affects the human mind in ways that are difficult to describe. You are surrounded by water, miles of it, in every direction, above, below, left, right. There is no escape, no quick exit. If something goes wrong, help cannot reach you in time. Inside the submersible, space is extremely limited. You cannot stand, cannot stretch, cannot move freely. You sit in a fixed position for hours. Your legs cramp, your back aches, but there is nowhere to go. Nothing to do but wait and monitor instruments. The descent itself takes hours, slowly sinking through layers of water. Watching the depth gauge numbers climb. 1,000 meters, 2,000, 3,000. The light fades gradually. Blue turns to darkness. And then there is nothing outside the viewport except black. Some people find this calming. A rare opportunity to experience complete isolation. No phone, no email, no distractions. Just you and the instruments and the slow journey into depth. It is meditative, peaceful, a chance to disconnect from the noise of the modern world. But others find it unsettling. The darkness presses in, not physically, but mentally. Your brain, evolved to interpret visual information, struggles with the absence of light. It starts to fill in the gaps. You might see movement where there is none, shadows that do not exist, your eyes trying to make sense of nothing. The silence adds to the effect. In normal life, there is always some background noise. Traffic, wind, voices, electronics. But inside the pressure sphere, sound is muted. You hear the faint hum of life support, the occasional click of instruments, your own breathing amplified in the small space. Hours pass slowly. There is no sense of movement, no way to feel that you are descending. The only indication is the depth gauge, numbers incrementing steadily. But you cannot feel it, cannot sense it. Your body has no reference points. This sensory deprivation can cause disorientation. Your inner ear which normally helps with balance, has nothing to work with. Up and down become abstract concepts. You know intellectually which way is which. But your body does not feel it. Some pilots report strange experiences during long descents. A sense of floating, of disconnection from the physical, as if the mind separates slightly from the body. It is not dangerous, but it is unsettling, especially the first time it happens. When you finally reach the bottom, there is no dramatic change, no sense of arrival. The lights illuminate a small patch of seafloor. Sediment appears in the viewport. And that is it. You are there. But being there feels surreal. You are sitting in a small sphere of air, surrounded by water under immense pressure. Thousands of meters of ocean above you. The seafloor beneath you has not seen sunlight in millions of years. Will never see sunlight as long as the ocean exists. You are utterly isolated. The surface is hours away. Communication is limited to slow acoustic signals. If something fails, there is no rescue coming. You are on your own. The sphere of metal and the knowledge of the engineers who built it are all that stand between you and instant death. That awareness sits in the back of your mind, not as panic, but as a quiet understanding of reality. You are in a place humans were never meant to be. You are surviving only because of technology, only because every system is working correctly, and any failure means the end. For some, this creates intense focus. Every sound is important. Every reading on every instrument gets attention. You become hyper-aware, alert to any change, any anomaly, because anomalies at this depth can be fatal. For others, it creates a kind of fatalism, an acceptance. If something goes wrong, there is nothing you can do. So you might as well relax. Trust the equipment, trust the training, and focus on the mission. The return journey brings its own psychological challenges. The ascent takes just as long as the descent. Hours of sitting, waiting, hoping that the buoyancy systems work correctly, that the ballast drops when it should, that nothing jams or fails. You rise slowly through the darkness. The depth gauge numbers decrease, but there is still no sense of movement, no way to feel that you are ascending. You simply trust the instruments, trust the process, and wait. When light finally appears, faint at first, then brighter, it feels almost unreal, as if you are emerging from a dream. The blue of the ocean at intermediate depths seems impossibly vivid after hours of blackness. Colors return, and with them, a sense of normalcy. The moment the hatch opens and fresh air floods in is described by almost every pilot as overwhelming. The smell of the ocean, the sound of wind and waves, the sight of the sky. After hours in darkness, the surface world feels intense, almost too bright, too loud, too much sensory input all at once. Many people need time to readjust, to process what they experienced. The return to normal life does not happen instantly. For some, it takes days. For others, longer. The experience of the deep stays with them, changes how they see the world. Some describe it as perspective. After sitting at the bottom of the ocean, everyday concerns seem smaller, less urgent. Traffic jams, work deadlines, arguments. All of it feels trivial compared to the weight of water and darkness they experienced. Others describe a sense of connection, realizing that the ocean covers most of the planet, that we live on a thin surface layer of a world mostly made of water, and that beneath that familiar surface lies a realm we barely understand. A few describe something closer to existential reflection. Confronting isolation at that level forces you to think about existence itself, about what it means to be human, to be alive, to be conscious in a universe that is mostly empty space and dark water. These psychological effects are not often discussed in technical reports, but they are real, and they affect how people approach deep-sea exploration. Some pilots do one dive and decide they never want to do it again. Not because it was dangerous, but because it was too intense, too isolating, too confronting. Others become drawn to it. They want to return, to experience that depth again, to sit in that darkness and feel small in a way that nothing else makes them feel. It becomes almost addictive. Not the danger, but the perspective. This psychological dimension is another reason exploration is limited. You cannot train someone to handle the isolation if they are not naturally suited to it. You cannot force someone to be comfortable in an environment that triggers deep instinctive fears. Fear of darkness is primal. Fear of enclosed spaces is common. Fear of being underwater, unable to breathe freely, unable to escape, is hardwired into our survival instincts. Deep-sea exploration triggers all of these fears at once. Only a small percentage of people can set those fears aside, can function effectively in that environment, can remain calm and focused when every instinct screams that they are in danger. This limits the pool of potential explorers, and it means that even when funding is available, even when technology is ready, finding people willing and able to make the journey is a challenge. The psychological barrier is just as real as the physical one, and in some ways, it is harder to overcome. You can engineer a solution to pressure, but you cannot engineer away the human mind's response to isolation and darkness. And so the trench remains not just physically remote, but psychologically distant as well. A place that exists not only at the edge of what our technology can reach, but at the edge of what our minds can comfortably process. The deep ocean is often described as silent, but this is not entirely accurate. What we mean is that it is silent to us, that our ears, adapted to hear through air, cannot interpret what is happening in the water. But the ocean is full of sound, and at depth, sound becomes one of the primary ways that information travels. Because light fails, because vision ends, but sound continues. It moves through water faster than through air, and it travels farther. In air, sound moves at about 343 meters per second. In water, that speed increases to about 1,500 meters per second, more than 4 times faster. This means that sounds carry across enormous distances in the ocean. A whale's call can travel hundreds of miles. An earthquake can be heard across an entire ocean basin. At the bottom of the Mariana Trench, sound behaves in ways that seem almost strange. The density of water under pressure is extreme, and that density affects how sound waves propagate. Low frequency sounds travel particularly well. They lose less energy to absorption. They bend less around obstacles. This creates an acoustic environment unlike anything on land. Vibrations from distant sources reach the trench and linger. The rumble of tectonic plates shifting, the groan of undersea landslides, the crack of ice breaking in polar regions thousands of miles away. Scientists have placed hydrophones in deep water. These underwater microphones listen constantly, recording everything. And what they hear is a complex soundscape. Not silence, but a layered mix of natural and sometimes human-made noises. Whales communicate at frequencies that propagate well through water. Blue whales, the largest animals on Earth, produce calls that can be heard across entire ocean basins. These calls are low frequency, deep, resonant. They travel through the water as pressure waves, bending around islands, following ocean currents, reaching depths where no light ever penetrates. A whale at the surface can send a call that reaches the bottom of the trench. The sound arrives distorted, delayed, but recognizable. To the creatures living there, this is part of the normal acoustic environment. A reminder that the surface world exists, even if they never see it. Fish also produce sounds. They click, grunt, scrape. Many species have specialized organs for making noise. Swim bladders that vibrate, bones that rub together, muscles that contract rapidly. These sounds are used for communication, for mating, for territorial disputes. Even invertebrates contribute. Snapping shrimp create loud clicks by collapsing their claws rapidly. The sound is sharp enough to stun small prey, and loud enough to be heard from significant distances. In some coastal areas, the collective noise of thousands of snapping shrimp creates a constant crackling background, like static. But perhaps the most interesting sounds come from the Earth itself. The ocean floor is not static. It shifts, cracks, groans. Tectonic plates move slowly but constantly. And when they move, they make noise. Earthquakes generate intense acoustic energy. The vibrations travel through rock and water alike. A major earthquake can be detected by hydrophones thousands of miles away. The sound arrives as a low rumble, building slowly, fading gradually. The signature of rock breaking deep underground. Volcanic activity also produces sound. When magma rises through cracks in the ocean floor, it superheats the surrounding water. The rapid expansion creates pressure waves. These waves propagate outward, carrying the news of eruption to any listener capable of detecting it. Underwater landslides, though rare, are catastrophic events. When sediment on a steep slope becomes unstable, it can collapse. Thousands or millions of tons of material sliding down the continental shelf. The noise is overwhelming. A roar that travels for hundreds of miles, announcing disaster to the entire ocean. Human activity adds its own layer to the soundscape. Ship engines produce constant noise. Propellers churn the water, creating turbulence and vibration. Sonar systems send out powerful pings. These sounds are loud, intrusive, and they travel far. In some regions, shipping lanes are so busy that the background noise has increased significantly over the past century. What was once a relatively quiet ocean is now filled with the constant hum of machinery. And this affects marine life. Whales that rely on sound for communication find it harder to be heard over the noise. Their calls get drowned out. They must sing louder or repeat themselves more often. This takes energy, and energy, especially in the deep ocean, is precious. Some species have changed their behavior. They call at different frequencies or at different times of day, trying to find acoustic windows when human noise is lower. It is adaptation, but it is also evidence of impact, of how our presence, even indirectly, changes the environment. The Mariana Trench, despite being remote, is not immune to this noise. Sonar signals from naval exercises have been detected there. The engines of research vessels, even the faint vibrations of commercial shipping lanes far above reach down into the depths. For scientists studying the trench, sound is both a tool and a subject of study. They use sonar to map the seafloor, acoustic positioning to track the location of submersibles, and they listen to the ambient noise to understand what processes are occurring. But interpreting underwater sound is challenging. It bends as it passes through layers of water with different temperatures and salinities. It reflects off the surface and the seafloor. It scatters when it encounters obstacles. By the time a sound reaches a hydrophone, it may have traveled a complex path, bouncing multiple times, arriving distorted. Signal processing helps. Computers can filter out noise, enhance weak signals, identify patterns, but some sounds remain mysterious. Recordings that do not match any known source. Noises that appear suddenly and then vanish. The ocean still holds acoustic secrets. One famous example is called the bloop, recorded in 1997 by hydrophones in the Pacific. It was a powerful, low-frequency sound, louder than any known biological source. The pattern suggested something alive, something massive, but no animal has ever been confirmed to produce such a sound. Later analysis suggested it might have been an iceberg fracturing or an underwater landslide. But the mystery persists, because the ocean is vast, and our ability to monitor it is limited. Most sounds go unrecorded, unnoticed, lost in the vastness of water. In the Mariana Trench, the acoustic environment is defined by stillness, punctuated by occasional events. Most of the time, the water carries only faint vibrations. The distant calls of whales, the slow settling of sediment, the almost imperceptible movement of water molecules under pressure. But then something happens. An earthquake, a landslide, the passage of a submersible with its thrusters and machinery, and the stillness breaks. Sound fills the water, travels outward, reaches creatures that have been waiting in silence, and then fades. The silence returns, but it is not empty. It is full of potential, of information waiting to be transmitted, of vibrations ready to carry meaning across impossible distances. For the creatures living at depth, sound is more important than vision. They sense pressure, waves with specialized organs, lateral lines running along their bodies, sensitive hairs that detect the slightest movement in the water. They live in an acoustic world, where survival depends on hearing what is coming before it arrives. To them, the ocean is not dark. It is invisible, but it is not silent. It is speaking. in frequencies and patterns that we are only beginning to understand, in a language written in vibration and echo, and the subtle physics of pressure, waves moving through dense fluid. And in that language, the trench communicates, not with words, but with the grammar of physics, the vocabulary of geology, the syntax of life adapted to conditions we can barely imagine. Sound in the deep is not just noise. It is connection. It is information. It is the way a vast, dark, isolated world remains tied to everything else, through vibrations that travel unseen, through echoes that carry meaning, through the simple fact that movement creates waves, and waves can be heard, even in the deepest silence. So where do we go from here? What would it take to truly explore the Mariana Trench? To understand it not just in fragments, but as a complete system? The answer is not simple, and it is not cheap. But it is possible. With better technology, with sustained funding, with patience, the trench could reveal far more than it has so far. Autonomous vehicles represent one promising direction. Robots that can operate without human supervision, that can navigate on their own, make decisions, adapt to changing conditions. These machines could stay at depth far longer than crewed submersibles, days instead of hours, mapping larger areas, collecting more data. Some autonomous underwater vehicles, or AUVs, already exist. They are used for scientific research, for offshore industry, for military applications, but most are designed for shallower depths. A few hundred meters, maybe 1,000. Building an AUV that can reach the trench requires solving multiple problems. Power is one. Batteries must provide enough energy for extended missions, but they must also function in near-freezing temperatures, under extreme pressure. Current battery technology has limits here. Some engineers are exploring alternative power sources, fuel cells, thermal generators that extract energy from temperature differences in the water, even biofuel systems that could theoretically run on organic material collected from the seafloor. These ideas are still experimental, but they show the direction research is moving. Navigation is another challenge. GPS does not work underwater. Radio signals cannot penetrate. So AUVs must rely on inertial navigation, using accelerometers and gyroscopes to track movement. But these systems drift over time, accumulating errors. After hours of navigation, an AUV might be hundreds of meters off course without knowing it. Acoustic positioning helps. Beacons placed on the seafloor can send signals. The AUV measures the time it takes for those signals to arrive, and calculates its position based on the distances to multiple beacons. But this requires infrastructure. Beacons must be deployed, maintained, recovered. It adds cost and complexity. Artificial intelligence may provide solutions. Machine learning algorithms can help AUVs recognize obstacles, identify interesting features, make decisions about where to go next without waiting for instructions from the surface. This kind of autonomy is critical for exploration, because communication delays make real-time control impractical. Imagine an AUV programmed to search for hydrothermal vents. It could follow gradients of temperature and chemicals, moving systematically through areas where vents are likely to exist. When it finds something interesting, it could stop, collect samples, take detailed images, all without human input. This is not science fiction. Prototypes already exist for shallower depths. Extending this capability to the trench requires better sensors, more robust programming, and extensive testing. But it is achievable. Another approach involves swarms of smaller vehicles. Instead of one large, expensive AUV, you deploy many smaller ones. Each carries limited sensors and equipment, but together they can cover large areas. If one fails, the others continue. The mission does not depend on any single unit. This distributed approach reduces risk, and it makes exploration more efficient. Multiple vehicles can map different areas simultaneously, compare data, work cooperatively to achieve goals that would take a single vehicle much longer. Communication between vehicles in a swarm is another technical challenge. Acoustic signals work, but bandwidth is limited. The vehicles must coordinate using minimal information. Simple status updates, position reports, priority signals when something important is found. Complex data gets stored locally and retrieved later. Materials science also plays a role in the future of exploration. New alloys and composites are being developed that can withstand greater pressure with less weight. Some are inspired by biological materials, the shells of deep-sea organisms, the structures of diatoms. Nature has spent millions of years solving these problems. Engineers are learning from those solutions. Carbon fiber composites reinforced with ceramic particles show promise. They are light, strong, and resistant to pressure. Some experimental pressure hulls have been built using these materials. Testing is ongoing, but initial results are encouraging. Glass is another material under investigation. Specifically, thick spheres of borosilicate glass. Glass, when formed into a perfect sphere, distributes pressure extremely well. And unlike metal, it does not corrode. Some scientists believe glass spheres could be used as pressure housings for cameras and electronics. Cheaper and more reliable than titanium. The design of submersibles is also evolving. Traditional spheres are being supplemented with other shapes. Cylinders with hemispherical ends, torus shapes, even irregular geometries optimized by computer modeling. The goal is to maximize interior space while maintaining pressure resistance. Modular designs are another concept. Instead of building a single integrated vehicle, you create separate modules. Each module serves a specific function. One contains batteries. Another holds sensors. A third carries propulsion. These modules connect together. And if one fails, it can be replaced without rebuilding the entire system. This modularity extends to missions as well. You could configure a vehicle for mapping on one dive, then reconfigure it for sample collection on the next. Swap out instruments, change payloads, use the same basic platform for multiple purposes. But technology alone will not expand exploration. Funding matters just as much. And funding requires public interest. People need to care about the deep ocean, to see value in understanding it, to support the allocation of resources toward exploration. This is where storytelling becomes important. When scientists share what they find, when images from the trench reach the public, when people see the strange, beautiful creatures living in darkness, it creates curiosity. And curiosity can lead to support. Some organizations are working to make deep-sea exploration more accessible, not just to scientists, but to educators, to filmmakers, to anyone interested in documenting the ocean. High-quality cameras, live streaming technology, the ability to broadcast a dive in real time. These tools help bring the trench to people who will never visit it personally. Virtual reality may play a role as well. Imagine putting on a headset and experiencing a dive to Challenger Deep, not as a passive video, but as an immersive simulation. You control where to look, what to focus on. The sense of presence would be far greater than watching on a screen. This kind of technology could help people understand what the trench is really like. The isolation, the darkness, the scale, and understanding might lead to appreciation, and appreciation to support. International cooperation is also critical. No single country has the resources to explore the trench thoroughly. But together, nations could pool equipment, share data, coordinate missions. This requires trust, diplomacy, agreements that transcend political boundaries. The ocean does not recognize borders. The trench does not belong to any nation. It is part of the global commons, and exploring it should be a shared human endeavor. Not a competition, but a collaboration. Some progress has been made in this direction. International research programs exist, data sharing agreements, joint expeditions. But more could be done. Much more. Private exploration is another possibility. Wealthy individuals have funded expeditions in the past, and some continue to do so. Their motivations vary. Some are driven by curiosity, others by the challenge, some by a desire to contribute to science. Private funding can move quickly. It is not constrained by government budgets or bureaucratic processes, but it is also unpredictable, dependent on the interests and resources of individuals. Not a sustainable model for long-term systematic exploration. The ideal future combines public and private resources. Government agencies provide baseline support. Universities conduct research. Private individuals fund specific projects. And together, these efforts create a sustained program of exploration that advances year by year. But even with perfect funding and technology, some questions will remain unanswered. The trench is simply too large, too complex, too dynamic. We will never know every detail, never catalogue every species, never map every square meter. And perhaps that is acceptable. Perhaps complete knowledge is not the goal. Perhaps the goal is understanding, knowing enough to see patterns, to grasp how the system works, to appreciate the trench not as a collection of facts, but as a living, dynamic part of the planet. That understanding is within reach, closer now than ever before. Each new dive adds pieces to the puzzle. Each sample reveals something unexpected. Each image shows us something we have never seen. The future of exploration is not about conquering the trench. It is about learning to listen to what it is already telling us. About building tools that can hear, that can see, that can withstand the pressure long enough to bring back stories. And those stories will change how we think about Earth, about life, about the limits of survival. They will remind us that our planet is stranger and more resilient than we imagined. That even in the harshest environments, life finds a way. And that mystery, real genuine mystery, still exists in abundance. The trench will never be fully explored. Not in our lifetimes. Probably not ever. But it will be better understood. More deeply appreciated. More carefully protected. And that might be enough. There is something profound about a place that resists understanding. The Mariana Trench is not mysterious because it is far away. It is mysterious because it operates under rules that do not apply anywhere else we know. And in that difference lies valuable lessons. The first lesson is humility. We live in an age of extraordinary technological achievement. We carry supercomputers in our pockets. We have mapped the human genome. We have sent robots to Mars. It is easy to believe that nothing is beyond our reach, that any problem can be solved with enough engineering. But the trench says otherwise. It reminds us that some environments are fundamentally hostile to human presence, that some places will always require enormous effort to visit, that we are, for all our cleverness, limited by biology, by physics, by the simple fact that we evolved for life on land, not in the deep ocean. This humility is useful. It prevents arrogance. It encourages respect for nature. And it reminds us that exploration is not about domination. It is about understanding our place in a much larger system. The second lesson is about patience. The trench has been forming for millions of years. The creatures that live there evolved over timescales we struggle to comprehend. The processes that shape the seafloor happen slowly, incrementally, without urgency. Our culture tends toward impatience. We want results quickly, answers immediately, progress that can be measured in weeks or months. But the trench does not work on that timeline. It teaches us to slow down, to accept that some knowledge takes time to acquire. That understanding emerges gradually, not all at once. Scientists who study the deep ocean know this well. They spend years planning a single expedition, decades analyzing data from a handful of dives, careers devoted to understanding processes that unfold over centuries. This patience is not frustration. It is discipline. And it is necessary. The third lesson is about interconnection. The trench seems isolated, remote, separate from the rest of the world. But it is not. Water that reaches the bottom of the trench eventually circulates back to the surface. Nutrients that fall into the deep feed creatures that support larger ecosystems. Currents that pass through the trench influence climate patterns thousands of miles away. Everything is connected. And what happens in the deepest ocean affects life everywhere else. This interconnection means we cannot ignore the trench, cannot dismiss it as irrelevant because it is remote. Its health matters. Its ecosystems matter. The chemistry of its water matters. When scientists find plastic in amphipods from Challenger Deep, it is not just an interesting observation. It is proof that our actions have consequences far beyond what we can see. That pollution does not disappear. It spreads, sinks, accumulates, even in places we can barely reach. This should change how we think about waste, about consumption, about the assumption that the ocean can absorb anything we put into it. The trench is not a dumping ground. It is part of a system, and systems have limits. The fourth lesson is about resilience. Life in the trench endures conditions that would kill most organisms instantly. Extreme pressure, near freezing temperatures, complete darkness, scarce food. And yet life persists. Not just survives, but thrives. This resilience is inspiring. It shows that adaptation is possible, even in the most unlikely environments. That evolution can solve problems we would consider insurmountable. That given enough time, life finds ways forward. But resilience has limits. The creatures of the trench are adapted to their environment. They are not adapted to rapid change, not adapted to chemical pollutants, not adapted to warming water or acidifying oceans. If the environment shifts faster than evolution can respond, resilience fails. This is the precarious balance. Life is tough, but not invulnerable. And human activity is changing the ocean faster than at any time in history. The question is whether the trench and the life it contains can adapt quickly enough, or whether we are pushing past the limits of what resilience can handle. The fifth lesson is about value. The trench does not produce anything we can extract. It has no mineral wealth worth mining, no oil reserves, no commercial fisheries. By conventional economic measures, it is worthless. A deep hole in the ocean floor that costs money to study and provides no obvious return. But value is not only measured in dollars. The trench has scientific value. It helps us understand plate tectonics, ocean circulation, the limits of life. These are questions worth answering, not because they lead to profit, but because they expand knowledge. It also has intrinsic value. The trench exists. That alone makes it worth protecting, worth studying, worth respecting. We do not need to justify its existence by finding uses for it. Its existence is justification enough. This perspective challenges how we often think about nature as a resource to be exploited, a system to be managed for human benefit. But the trench suggests another view, that some places are valuable simply for being what they are. That preservation is its own reward. The sixth lesson is about perspective. Standing on land, looking at the ocean, it is easy to forget what lies beneath. The surface looks calm, familiar, safe, but beneath that surface is an alien world. Deeper than mountains are tall, darker than space, more hostile to human life than almost anywhere else on Earth. This hidden world is part of our planet. Most of the biosphere exists in the ocean. Most of the ocean exists in depths we cannot visit. And that means most of the living space on Earth is unknown to us. We are, in a very real sense, living on the roof of our planet, unaware of what lies in the basement. That perspective is humbling. It reminds us how much we do not know, how much remains to be discovered, how limited our experience of Earth really is. We think we know our planet, but we barely know its surface. The volume beneath the surface is mostly mystery. The seventh lesson is about time. The trench connects us to deep time, geological time, evolutionary time. The rocks at the bottom of the trench are millions of years old. The sediment contains records of ancient climates, ancient extinctions, ancient processes that shaped the world long before humans existed. This long view is rare in modern life. We focus on the immediate, the urgent, the now. But the trench reminds us that Earth operates on timescales that dwarf human history, that our species is recent, our civilization a blink, and the processes that created the trench will continue long after we are gone. This is not depressing. It is perspective. It shows us where we fit in the story of the planet. Not at the center, not as the culmination, but as one chapter among many. Important to us, but not to the Earth, which was here before us, and will be here after. The eighth and final lesson is about wonder. In an age where information is instant and answers are expected immediately, wonder is a rare commodity. We have become accustomed to knowing, to having access to explanations for everything. But the trench preserves wonder. It is a place where questions outnumber answers, where mystery is real, where the unknown is not a temporary state, but a permanent condition. And that is valuable, because wonder is what drives curiosity, and curiosity is what drives exploration. When we stop wondering, we stop learning. When we assume we know everything, we stop looking for more. The trench ensures that we keep wondering, keep questioning, keep searching, because no matter how much we learn, there is always more waiting in the deep. These lessons are not taught explicitly. The trench does not speak in words. It does not offer lectures. But through its mere existence, through the challenges it presents and the mysteries it holds, it teaches nonetheless. And the students are those willing to pay attention, to look beyond the surface, to ask what lies beneath, to accept that some things will always be partly unknown, and to find meaning in that unknowability. There is a strange parallel between the ocean and the human mind. Both have surfaces that seem familiar, and depths that remain hidden. We spend most of our lives on the surface, moving through thoughts and experiences that we can easily name and understand. But beneath that surface lies something else. The unconscious mind. The parts of ourselves we do not directly access. Memories buried too deep to recall easily. Emotions that emerge without clear cause. Dreams that follow logic we cannot trace. All of this exists in a kind of internal depth, pressurized by time, hidden in darkness. When psychologists talk about exploring the mind, they use depth metaphors. Going deeper, uncovering buried feelings, bringing things to the surface. The language reflects how we understand consciousness, as layered, with accessible parts above and mysterious parts below. The Mariana Trench mirrors this structure. The surface of the ocean is where most life happens, where sunlight reaches, where interaction is constant. But the trench is the unconscious of the ocean, the part that operates invisibly, that shapes currents and chemistry without anyone noticing. And just as the trench is difficult to explore physically, our inner depths are difficult to explore mentally. They resist easy access. They require special tools, patience, the willingness to sit with discomfort and uncertainty. When someone descends into the trench, they often describe the experience as introspective. The isolation, the darkness, the silence, all of it creates a state similar to deep meditation, where external stimuli fade and internal awareness increases. You become aware of your own breathing, your own heartbeat, the small sounds of your body functioning. In that state, thoughts drift differently. Without distractions, the mind turns inward. And sometimes, things surface that were buried. Memories, feelings, realizations that were always there, but hidden under the noise of daily life. This is not unique to deep-sea exploration. Long-distance solo sailors report similar experiences. Astronauts on extended missions. Anyone who spends significant time in isolation with limited sensory input. The mind, deprived of external focus, begins to explore itself. The trench facilitates this in a particularly intense way, because the isolation is total, the darkness absolute. There is no possibility of distraction, no way to look away from whatever arises internally. You sit with it, experience it, and eventually you return to the surface changed. Not everyone welcomes this. Some find the introspection uncomfortable, prefer to stay busy, keep their attention focused outward. But for others, it is the most valuable part of the experience. Not the scientific data collected, not the images captured, but the internal journey that happens in parallel with the physical descent. Water itself is symbolic of the unconscious in many traditions. Deep water, dark water, still water, all represent hidden aspects of the psyche. When we talk about emotional depth, we use water metaphors. Feeling overwhelmed, drowning in sadness, coming up for air. The language links water and inner experience. The trench takes this symbolism to its extreme. It is the deepest water, the darkest, the most still. It represents the furthest reaches of the unconscious, the places within ourselves we rarely visit, the experiences and memories and parts of identity that remain submerged under the weight of daily consciousness. Exploring the trench, then, becomes a way of exploring ourselves. Not literally, but metaphorically. Each descent is a journey into hidden territory. Each return brings something back. Not always clear, not always comfortable, but always significant. This parallel extends to fear as well. The trench frightens us because it represents loss of control, loss of visibility, loss of the familiar reference points that keep us oriented. And these are the same things that frighten us about our own depths. We fear losing control of our emotions, fear what might emerge if we look too closely at buried memories, fear the parts of ourselves we do not understand. The trench externalizes those fears, makes them physical, and in confronting them physically, we sometimes confront them internally as well. There is also the question of pressure. The trench exists under immense pressure, and so do we. The pressure of expectations, of responsibilities, of past traumas and future anxieties. All of it presses down constantly, shaping who we are, how we function, what we can tolerate. Just as creatures in the trench have adapted to physical pressure, we adapt to psychological pressure. We develop coping mechanisms, build internal structures that distribute the load, find ways to function despite the weight. But the pressure never disappears. It becomes part of the environment we live in. When that pressure increases too quickly, we experience what divers call the bends, a sudden release of pressure that causes internal disruption. In psychological terms, this might be a breakdown, a crisis, a moment when the structures we built to handle pressure fail. Recovery requires careful decompression, slowly releasing the pressure, allowing time to adjust. The same is true emotionally. We cannot fix everything instantly, cannot rush healing. It requires patience, time, gradual adjustment to new conditions. The trench teaches this implicitly. You cannot ascend too quickly from the depths. You must rise slowly. Allow your body to adjust. And the same principle applies to exploring difficult emotions or memories. You cannot force insight, cannot rush understanding. It emerges slowly, as you are ready to integrate it. There is also beauty in the deep, both in the ocean and within ourselves. The bioluminescent creatures glowing in the darkness, the unexpected adaptations, the resilience of life in harsh conditions. All of this mirrors the beauty we can find in our own depths when we look carefully. Hidden strengths, creativity that emerges from darkness, wisdom born of difficult experiences. These are the lights that glow within. Not bright, not constant, but real, and valuable precisely because they developed in conditions that seemed impossible. When people return from a dive to the trench, they often struggle to articulate what the experience meant. The scientific findings are easy to describe, but the personal impact is harder. It exists in feelings more than words, in shifts of perspective that are subtle but lasting. They see themselves differently, smaller in some ways, part of something much larger, but also more resilient. If they can sit in that darkness and return, what else can they handle? What other fears might be less frightening by comparison? This is the gift of exploring the deep, whether in the ocean or within ourselves. It shows us that we can survive discomfort. That darkness is not the same as danger. That isolation can be productive rather than destructive. And that the journey into the unknown, while frightening, is also where growth happens. The trench exists physically, but it also exists symbolically, as a reminder of what lies beneath all surfaces, as an invitation to explore not just the planet, but ourselves, to sit with discomfort, to accept mystery, to recognize that depth, whether in water or in consciousness, is where the most interesting discoveries happen. And perhaps that is the deepest lesson the trench offers. That exploration is always both external and internal. That understanding the world and understanding ourselves are not separate pursuits. That every journey outward is also a journey inward. And that the two inform each other in ways we are still learning to articulate. If you close your eyes and imagine the trench now, what do you see? Or rather, what do you not see? There is no light, no color, no movement except the slow drift of particles through water too thick to call fluid. The pressure is constant, the temperature steady, the darkness deeper than any darkness you have known. And beneath it all, a silence that is not empty but full full of waiting, full of presence, full of time moving so slowly it almost stops. This is where our journey ends. Not with answers, not with certainty, but with an image, a feeling, an understanding that some places exist beyond our reach, not as failure, but as fact. The Mariana Trench will never be fully explored. Not in our lifetimes. Perhaps not ever. The barriers are too fundamental. The costs too high. The environment too hostile. And perhaps that is exactly as it should be. We have mapped the land, charted the skies, reached into space, but the deepest ocean remains mostly unknown. And in that unknowing lies something valuable. A reminder that mystery still exists, that the world is larger than our understanding, that some places can simply be, without needing our complete comprehension. The creatures at the bottom do not know they live in the deepest place on Earth. They do not know we exist. They simply live, day after day, year after year, following rhythms set millions of years before humans appeared. And they will continue long after we are gone. They do not rush. They do not compete unnecessarily. They exist in balance with their environment because there is no other option. Every movement carefully measured. Every calorie conserved. Survival not through dominance, but through patience. That balance is worth contemplating. Not because it is beautiful, though it is, but because it is stable. The trench does not change quickly. What happens there happens slowly, over scales of time that make human lifetimes seem like single breaths. In a way, the deepest part of the ocean is the calmest part of the planet. No storms reach it. No sunlight disturbs it. No seasons change its rhythm. It is a place where urgency does not exist, where the frantic pace of surface life cannot penetrate. We cannot live there. Our bodies are not built for it. Our minds not adapted to that much isolation. But we carry something of it within us. The same elements that make up the ocean are in our blood. The same minerals that rest on the seafloor are in our bones. The same water that fills the trench flows through our cells. We are connected to it, whether we visit or not, whether we understand it or not. The trench is part of Earth, and we are part of Earth. The connection exists independent of awareness, independent of technology, independent of exploration. And maybe that is the final truth about the Mariana Trench. It does not need to be explored. It does not need to be understood. It simply needs to exist. As a reminder, as a mystery, as a quiet, dark, patient place that holds the memory of the planet itself. Somewhere beneath the Pacific Ocean, 7 miles down, that place continues. It will continue long after this moment. Long after anyone reads these words. Long after our civilization has faded into the same sediment that covers the seafloor. The trench does not care. It does not watch. It does not wait for anything in particular. It simply is, moving slowly, breathing softly through geological time, existing in a present that stretches across millions of years. And in its existence, it teaches the same lesson it has always taught, that some things are too deep to reach fully, too vast to measure completely, too quiet to hear clearly, and that this is not a problem to be solved. It is a fact to be accepted. That acceptance brings its own kind of peace. The peace of knowing your limits, of recognizing what you can and cannot do, of understanding that mystery has value, that the unknown serves a purpose, that not everything needs to be brought into the light. The deep ocean will remain deep. The trench will remain a trench. And we will remain surface dwellers. Looking down into darkness, we can visit but never inhabit. Wondering what lies there. Imagining what it would feel like to sit in that pressure and that silence. But imagination is its own form of exploration. It costs nothing, risks nothing, and reaches places no machine can go. In imagining the trench, we touch something real, something that exists beyond data and images, something that speaks to the part of us that recognizes depth when we encounter it. So as you drift towards sleep now, carrying this story with you, let the image of the trench settle into your mind. The darkness, the pressure, the stillness. Let it become a place you can visit internally. A space of quiet, of depth, of mystery that does not demand answers. And know that somewhere, far below the surface of the ocean, that place continues. Untouched by your thoughts, unchanged by your awareness. Simply being what it is, what it has always been, what it will always be. The deepest quiet on earth, the lowest point, the final depth, where pressure becomes presence, where darkness becomes weight, where silence becomes the only language that matters. And in that quiet, the planet breathes, slowly, steadily, without concern for anything above or beyond. Just existing, just being, just continuing in the way only the deep can continue. Forever patient, forever dark, forever deep.